Hello! Magandang umaga sa lahat.
Hi, good morning.
May buntag sa atong mga amigo diha sa mga taga-Visayas and Mindanao. Good morning to all participants in the USA, Europe, and other part of the world. It is my pleasure to welcome you all for joining the parallel session 5.2. This is the computer science, machine learning, and artificial intelligence as part of the 40th PAASE anniversary and 2020 APAMS, that is Annual Scientific Meeting in the Philippines. In this session, we have 10 distinguished speakers from Asia, Europe, and the United States that will discuss the research on artificial intelligence, application towards robotics, particularly driverless cars, unmanned aerial vehicles, bomb disposal robot, vertical farms, sustainable energy, and traffic management for smart city. I am your host, Elmer P. Dadios, a professor and university fellow of De La Salle University, Manila, and thank you for joining us this session. So our first speaker, this is an invited speaker for today, is Dr. Marcelo Ang. He received his Bachelor of Science and MS degree in Mechanical Engineering from the De La Salle University in the Philippines and University of Hawaii, USA, in 1981 and 1985, respectively. And his PhD in Electrical Engineering from the University of Rochester, New York, in 1988, where he was an assistant professor of electrical engineering. In 1989, he joined the Department of Mechanical Engineering of the National University of Singapore, where he is currently an associate professor and acting director of the Advanced Robotics Center. His research interests span the areas of robotics, mechatronics, autonomous systems, and applications of intelligent systems. He teaches robotics, creativity and innovation, applied electronics and instrumentation, computing design, and related topics. In addition to academic and research activities, Dr. Ang is also an active involved in the Singapore Robotic Games, which he is the founding chairman. And is also the member of the Advisory Council of the World Robotic Olympiad. My friends, ladies and gentlemen, it is my pleasure to present to you Dr. Marcelo Ang.
Thank you, Elmer. Good morning, everybody. I'm very happy to be here to share with you all the developments in robotics and hopefully to encourage you to see the potential of robotics in improving the quality of our lives. I just shared my screen. I trust you can see it. The resolution may not be very good because I optimized it for video playing. So I use the word general intelligence and to see really the challenge today in making the robot more intelligent. And I'll explain more later on. Let's look at the technology and how it has helped in our daily lives. First is the mechanization. It's a new term. Let's call it Industry 1.0, where there is steam instead of human hands. There is water that will make things move. Then Industry 2.0 is the invention of electricity. So we don't need to rely on water or steam anymore. We can easily transmit power through electrical lines. This is powering machines. And in the birth of computers in the 1950s and 60s, there's Industry 3.0, where we now use computers to have more intelligence, or the first form of intelligence, which are programmable machines. This is Industry 3.0, where you have IT starting to develop also and on machines. And we see how IT has really influenced our daily lives today. When computers were first invented, the first uses were heavy computation and perhaps weather forecasting and military applications during those days by where DARPA created the computers. And nobody thought at that time, or many thought, even IBM's Watson thought, there's no room for computer in our daily homes, in our homes or every day. But today, we see computers very much part of our daily lives. We carry it every day with us in the form of a mobile phone with a very high computational power, right? And the most use of IT today is not weather forecasting, high-end computation, but perhaps is social media, right? And also communications. Who would have thought in the 1950s that computers would be used for such a purpose? Today, we are Industry 4.0, where the intelligence has increased due to the increasing power of computers, paralleled with developments in data, right? I mean, availability of data, I mean. And today we are at the stage where perhaps we're starting to see a tipping point where robots are not only in the factories, similarly like what people thought computers were only in weather forecasting or military application of big companies, but perhaps robotics and computers on machines, right, will be part of our daily lives. So I will share with you what are needed to get really this to happen, and what we are doing, and also what the rest of the people are doing. So we are today in autonomous robots, where the key, comparing it with Industry 3.0, is the environment is no longer structured, it's unstructured. In the factory, it's fixed, everything is precise, there's no human being, like a lights out factory. But today, it's unstructured. If you visit my home, you know how unstructured it is. I lose many things. I don't know where things are. It's dynamic because humans are inherently messy people, because the world is built for human beings and we cannot separate humans and robots, right? So here's a diagram of really structured environment. You can see the person here outside with a cage. Once the person enters, the whole robotic system shuts down for safety, because this robot will continue to weld the car. It doesn't care whether there's human or not. If the car is replaced by a human, the human will be welded by the robot, and that's unsafe, definitely, right? So in this environment, the robot is intelligent, but it doesn't have external sensors. It has only internal sensors. So internal sensors means it's like feeling its own joints. It knows where its hands is. It's like humans, right? If you raise your hand or put your hand down, you will know, right? You don't need to open your eyes. So that's what the robot is operating on, internal sensors. And when we go to Industry 4.0, instead of in addition to internal sense, it has also eyes, so it can tolerate unstructured environments and operate better. So I call this everyday robotics. So we want to move from the left to the right, from structured human-robot separated environments to unstructured, where there's human-robot interaction, like in the hospital wards, in our daily home, in our homes, in the shopping aisle, in the shopping mall, right? So the challenge is, how do we move from factories designed for robots to really spaces designed for human beings, right? I don't want to compromise how I live, how my home looks like, to suit the robot. The robot must be able to adapt to the environment that is built for human beings. So the ultimate system perhaps is ultimate assistant, ultimate companion, ultimate co-worker that will help us. And this is the robot below, this is the human on top, and the robot needs some good body that's human friendly, and the brain for intelligence. And this will work in our society, working together in a mixed environment, meaning no human robot separating, where really the robotic system is the ultimate tool. And there are many everyday tasks where the robot can help us, not only in the factory is already working, but really in our home, entertainment, leisure, sports, healthcare. And I think the most compelling applications are the 5Ds in robotics. I call it Ds. And these are where tasks that humans ought not to do, because humans are too intelligent and it's no fun doing it. To make life more meaningful, we have to get rid of these Ds and get the robot to help us do these Ds. And the second is these Ds perhaps are tasks that robots can potentially do much better than human, right? Dangerous tasks, demeaning tasks, degrading tasks, dirty tasks for these. And about 10 years ago, I started to work on the 50, which is driving vehicles. We waste a lot of time driving vehicles, especially in places like Manila, where I grew up in. If traffic jam is there, right? It's kind of irritating to drive. But imagine if the car is self-driving, even if it's a traffic jam, you're connected, you're in your mobile office, you can do a Skype with your loved ones, we can do a virtual meetings like what we're doing now, presentation. So it's really, it doesn't really matter, right? Well, it's really fully connected. And when 5G comes on board, mainstream, it will be really much easier to do things like this. So driving vehicles is one. Now, in the rest of the talk, I'll focus only on the brain because the topic, I want to focus on intelligence, but there's also a whole set of topic, how to improve the body of the robot, so to make it human friendly and safe, right? So the brain does four things. It has to sense. It has, after it sense and to understand the environment, it has to plan what to do. And after it plans, it executes, and it learns continuously. And this loop happens all the time. And this happens using internal sensors. We're doing some planning without our eyes, and also using external sensors. So that brings to different levels of intelligence. The lowest level, running at 1 to 3 kilohertz using our internal sensors, and the upper level using our external sensors, right? Imagine the task is to draw a straight line using your hand, carrying a pen, for example. You can close your eyes while doing it, and you can imagine your hand is moving straight. Or in addition to that, you can open your eyes to make sure the hand moves straight, right? So we, in our body, in our human body, if you make it like a robot, right, we have a level of control that's happening in the lowest level and a level that's happening in the higher level. And actually, a human body or a complex robotic system will have many levels of control running at different loops, different speeds. The lowest is the fastest, going up to slowest and slowest. And the highest level may be strategizing, right? Strategizing, perhaps I want to be able to reach my goal. If I'm traveling, what should be the best path I should take? So I get there in the fastest time, then you plan. And as you plan, there may be a middle level, there's a roadblock, then you modify your plan and you do some decision making and you actuate your arms for proprioceptive internal control to turn the steering wheel and things like that. In a machine, the same low level and high level task is typically done using computers. The lowest level task is using a small microcontroller, similar to the smallest computer that you have in your mobile phone, that's running your, reading the GPS signals, reading the IMU, knowing when to turn the phone, landscape or portrait, and a higher level computer that's doing communications and high level planning. And that's the desired task. And there's always this typical hierarchy. In some computers, some systems, you may have 3 computers going from lowest level to higher levels. So let's focus about this loop, these 4 things I talk about: sensing, planning, execution, and learning, right? What are the 2 basic approaches of doing these 4 things? There is the model-driven approach of intelligence. A model means you describe a physical phenomena using a mathematical model relating inputs and outputs. And once you have that mathematical model, let's say that function, you can always use that function to design what is the input to create your desired output by doing an inverse mapping of the function. And that's how we control our world. That's based on our understanding. That's why we study science and technology, so we can model. That's very good, right? Now, if you look at your physical phenomena, right? If that is a human body, for example, my desired task is to walk. So what are the inputs to my muscles in my legs so I can walk from A to B? Now, to do that, to understand, we need to have a mathematical model of our human body. That means we need to model the many joints, more than 50 joints perhaps of our body. model our muscles, know my weight, know the mass distribution, know how blood flows, and everything. You can see how complicated that is to create a mathematical model. And people have tried that. You can search the internet, right? So it's not so effective, not so practical. And furthermore, humans can walk. Do we know the mathematical model describing our body? I would say no, but maybe it is yes, subconsciously, but I'm not sure. I don't think so. So that leads to another approach, which is a data-driven approach. We can also achieve the same task of walking by learning from experience. Perhaps that's how humans develop walking capability. A baby cannot walk. Once he or she turns 1 year old, he starts crawling, and the 2 year old, the toddler, will start walking, but not perfectly and falls down. And once he falls down, he learns from experience, and they later on gets better and better. So how do we learn from experience? What is experience? Experience means data. And how, and perhaps with the data, we create a data model rather than a physical mathematical model. So the question is which to use is better? And I think the answer is obvious, I think. We should use both. If we have a physical model based on Newton's law, for example, we should use it, but we know it's not accurate. So why don't we use data to make the model better, to improve it? But even if we don't have the model, we can still use data. This is like learning from trial and error. So how do we do this? People have started looking at the brain, understanding how the brain works. You have brain cells connected to each other where signals are transmitted from A to B, right? Using these axon connections, electrical signals. So can we model it using a computer? And in the earliest 1960s, Bernard Widrow from Stanford developed the Adeline, where he models the neuron with a summer. Getting inputs x1, x2, x3 creates an output. And depending on the magnitude of the output and the experience provided by the environment, let's say the human falling down, that is the teacher, these two inputs are going to another function. This is an activation function that looks like a step function and creates an output. So this step is like, is the neuron going to be very excited or very dormant or bored, right? So if it's bored, that means it sleeps. If it's excited, it's super excited, gives high, and that's the output. So that's a very primitive approximation of a neuron in our brain. So if we connect them together by using a multiple layer like this, then you get some remarkable intelligence, which is what we're seeing today, that humans can learn from experience, which provides the teacher, and how this is formed, and what are the parameters that describe this neural network. Now, this started in the 1980s, the multiple Adelines. Then it died in about 1990 to 2000 because of the excessive computing power needed. But today, because of the availability of graphics processing unit and a lot of massive computing that can be done in parallel, one, and second, because of the birth of internet, the availability of data, we all have Google Photos account, we share all our data. So the teacher is becomes a lot. So it has been revived from in starting from 2000, and they have called the neural network now deep neural networks, because before the layers were only 3 layers, maybe 100 neurons. Now we're talking about 10,000 neurons and hundreds of thousands of layers being done. So we are seeing massive results right now, which is perhaps at the tipping point to make really robots more intelligent. So in the following slides, I'll show you some videos of some of our work that try to do this. Okay. Uh, there's a problem. My screen just froze. Hello, can you still hear me?
Yeah, we can hear you, but the slide seems frozen.
Yes, my computer froze. The PowerPoint
Oh,
froze. I'm sorry about that. Let me try to figure out, but my computer is still okay because you can still hear me.
oh yes, yes, we can hear you.
Yeah, so let me, sorry about that. Let me try to manually kill the PowerPoint slideshow if I'm able to do that. Looks like I'm not able to kill it too. Uh, okay, I think what I'll do, I'm really sorry about this. I have to physically do a hard reset of my computer. So that would mean it will be, we have to take a break of about 2 minutes. I know we're running late, but I'm really sorry about this. This is
You,
technology.
Marcelo, you tried to stop share first and then share again.
Yeah, my computer is not
Ah,
responding.
doesn't. Okay.
Yeah, I cannot even do a task manager. I cannot even do a control alt delete. So I have to manually. So okay, sorry, I have to disconnect now.
Okay, while waiting for Marcelo, maybe the participants can ask questions also. So uh, you can put your you can write your questions in the chat, and then during question and answers, we will answer all those questions.
Morning, Doc.
Hello guys, good morning.
Morning, everyone.
We experienced the technical difficulties of Marcelo, so we're trying. He's trying to solve it, and he will be coming back.
Elder, I have a question that I type on the chat.
Edsel, you have a
Do you see my question? So
yeah.
when do we reach that point where the robots are creating their own robots and then we will all become useless? It's getting close, I suppose.
It's still very far, Edsel.
I think so.
It's still very far. I'd
Yeah,
say it is not in our generation.
you know, in the 1980s, 1970s, we said that artificial intelligence will never be able to create a program that will beat the top chess players. And in a span of 10 years, we developed the systems that beat the world champion in Go also. Yeah? So I think it's getting closer and closer. Yeah, but certainly let's hope that we will not all become useless somehow.
You bear in mind, we are the one who make the intelligence of these robots. So still the minds of the humans are the one.
That's true, but you know, when I look at these computer chess programs like Alpha Zero, the Alpha Zero that
yeah. Okay. So I am now the host. Wait. Oh, wait. Are you in now? Okay, Marcelo just called because he's coming. He's letting in now. So we'll wait.
While we're waiting, if I may comment on Edsel's remark about the concept of self-replicating robots or robots that are able to clone themselves. I think that's a very fascinating concept, and I'm sure that certain engineers probably are already thinking about that. But there certainly is a lot of ethical questions that need to be addressed first before that is allowed to happen.
Actually,
but that certainly is a very enticing concept.
What I think is not only cloning themselves, but creating better and better robots than the robots themselves.
Correct.
And the machine starts taking over somehow. But that's
that is a very interesting concept and idea, but I think that will never happen. And I think we can have a separate discussion of that. So sorry about that. Can I have about 10 more minutes? I know we're running late.
Okay, Marcelo, please go ahead.
Okay, thank you. So I will.
Elmer, I've got a question for you. Would it make sense for me to present while Marcelo is waiting?
Yes. Marcelo, are you ready, or we can?
I'm ready.
Okay.
Oh, is it? Okay, sorry. I thought he would need another 10 minutes. Sorry.
No. What I mean is I will take another.
Sure, Marcelo, go ahead.
To complete my presentation.
Okay.
Okay, so I just want to quickly show you some videos of how we're using this in our self-driving vehicle work. It's something like Grab. I want to go to a train station. I use my phone to go book a car. But then the golf cart comes in. Why is a golf cart? Because the car is still the roadside. And I'm too lazy to walk to the car. So I take a golf cart. And you can see on top what the sensors are seeing, how far ahead it's seeing. So it's going through a pedestrian environment. We call it multi-class autonomous vehicles because this is one class, a golf buggy. It goes inside the buildings because we do not rely on GPS because GPS is not accurate. And this
Marcelo, you have the wrong screen.
Oh, really?
Shared. Yeah.
Oh, sorry. Okay. How about now?
It's good now.
Okay, sorry about that. So you book it and it goes to the roadside where it starts. All our vehicles are named after and you know you have booked, you're going to the train station. Suppose that you have booked it, you enter the car and you confirm your destination. And you can, after entering the screen and confirming your destination, the car just drives itself. So this is one way we are doing self-driving capability, and we're trying to use a hybrid approach, traditional methods coupled with deep learning approach. Now and go to a next video. Singapore is planning to fully deploy such vehicles in 2022 in 3 areas. This is a Singapore public bus. We have put our algorithms in a public bus. Yes.
Can you lower down the background of your video?
Okay.
Let's hear you. want to listen what you're talking. So
Okay. Okay, so we are 3 towns are planned in Singapore, Jurong, Tengah, and Punggol, to have public buses that are driverless. We're working towards level 5 autonomy, that's physically there's no safety driver. Right, so this is a visualization. This is really how an actual Singapore bus looks like, how it sees the environment, how it sees the car around it. And we use LiDAR and cameras. We have 4 cameras right now, although we have more than that, but we only 4. It can classify objects around it, whether cars, trucks, pedestrians, motorcycles, public roads. The whole Western Singapore is already allowed for public testing of autonomous vehicles. We were very serious about this because we want to have an efficient public transportation system. And this is how the left and right left and right cameras are seeing, and also the back cameras. On the right, we're doing some primitive form of prediction, because to do planning, we need to know where the other cars will go in the next 1 to 5 seconds, and we plan our motion that way. So let me review. That is sense, plan, act, and learn. And one way is to learn from data. And learning from data is very easy, very good. We know how to do that, but it's not able to generalize. That means to know whether left and right are the same or not. The computer doesn't know that because it's not able to generalize, because the right has the same environment but with a lot of people. But humans know how to do that, right? If you go to a train station, whether there's crowded or not, you know what station this is. So how do we learn from data without memorizing the data? Unfortunately, today, all the deep learning neural networks tend to memorize data. It will understand, it will recognize you've seen it, but it doesn't know if you have changed it like what you've seen here. So that is a problem today. And the key is how do you design the correct network architecture, the hyperparameters that describe all these phenomena. So one way to do it is to show more. And this is a traditional approach. MRT is our train station to show different pictures of MRT stations at different environments, when it's crowded, not so crowded, at different viewpoints. And can we say that we know now it's Raffles Place MRT because of that? Another problem is rain. Sensors do not work in rain much. So we tried to see how we can use deep learning or neural network to remove rain. In other words, like for humans, we live enough in the world. So if we see an environment that's raining, we can imagine the same environment without raining. But we have a lot of data that's needed to train the neural network to learn this experience. So what we did is we use simulation to create fake rain. This is something like fake news. So we train it on synthetic data so that I can avoid asking my student to go in the rain and wait for the rain to record videos. So why don't we create rain artificially? And we have clean images, rainy images as a pair, left and right, and train the neural network that way. And that actually surprisingly works. And we tested it on real world data. You can see how the sensor data is on the left with rain corruption, and how we have used software to remove the rain so our sensors can work. Another way that we're trying to do, this is really what generalized intelligence is about, is to do away with pre-mapping. Many of the autonomous vehicles work we do is we need to be able to map the place beforehand before it can operate. But is it possible we just give a paper map like what's shown? So we don't need to have the vehicle go there beforehand. And once the vehicle sees a real scene, it will be able to do a correspondence. What's the difference between the real scene and this, and to know where we are. It's almost like you arrive at an airport, right? You get down off the plane, you go to the building, you look at a map of the building, of a map saying where baggage claim is, where immigration is. You don't need to be in the airport beforehand, but you will be able to read the map and associate that paper map with the actual scene that you're seeing with your own eyes. So this is something that we're doing today. And there's many more challenging tasks, like everyday tasks that we cannot do, like plugging something into a hole, opening a water bottle. Let's look at opening a water bottle. Can we train the neural network using data from opening, let's say, 3 kinds of water bottle? But by doing that, can it now learn to generalize and open all sorts of water bottles, right? The answer is still no. If we want the robot to open a door, right, there are many kinds of door. It's impossible to show them all possible doors, but can we give a representative set of doors so it will be open a door it hasn't seen before, right? There's no answer yet. The key is how to create the correct architecture of the neural network. How many neurons, how many layers, what are the activation functions that for each brain cell or neuron, and how to give it data to be representative of the whole world. Let me, this is my last video. This is some recent work that I want to show you of how we have sort of put things together and how robots can help humans. We use all open source low-level software. The robot can detect objects, everyday objects. We have to train this to detect cuboids or blocks and also bottles. It detects also the human hand. So wherever the human hand is, it will just pick up the bottle and put it there. So these are very primitive first steps in how we can build intelligence in the robot. This is the neural network we're using, YOLO and mass RCN to do object detection. Some primitive form of speech recognition and natural language understanding without going through a script, right? We have a vocabulary and a simple dictionary, and it tries to learn the concept rather than dictating what is the response.
What should I do with this gearbox?
Assemble this gearbox.
Sure. I mean, how to assemble this gearbox?
You should use a screwdriver to fasten 4 bolts on the box.
Okay,
and do you know where can I find a screwdriver?
Idea on how we're doing it, and thank you very much for your attention. And I'm sorry for the technical difficulties. That's why we never use Windows to control a robot. Yeah. Okay, let me stop sharing. And if we have, and I'm sorry, I think the next speaker is Joel. I'm sorry for that I've eaten up some of your time.
Okay, thank you, Marcelo, for that very interesting presentation. Yeah, it's so unfortunate that we encounter technical difficulties.
Yes, I'm sorry.
I'm afraid we cannot do with the question and answer now. Instead, let's just put the questions on the chat and then maybe we can answer it later.